Okay, so we're back, and our last speaker of the day is Schenck. Thank you, Hal, for accepting the invitation. Hal received his PhD from Cornell University and is currently a professor at Auburn University. His research interests include algebraic geometry, commutative algebra, topology, and applied mathematics. And today he will give us an introduction to multiparameter persistent homology. You need to unmute yourself. How?
So thanks very much for the invitation to speak. I know that it's 5:30 in Brazil, so I would encourage everyone. It's 3:30 here, so I can't have a glass of wine in my hand, but I hope that all of you are taking advantage of drinking a glass of wine with the talk. So what I'm going to do today, although it's titled Introduction to Multiparameter Persistent Homology, I want to start out and spend actually the bulk of the time on the one-dimensional case, because I think that the passage from one dimension to several dimensions is actually not as crucial as the basic setup. So here's the outline of the talk. So 0 will be motivation, the check complex, RIPS complexes. 1 is going to be turbo, algebraic topology, and simplicial complexes. So for those of you that are already sort of advanced students of algebra and topology, this will be a review, but this will make sure that we're all on the same page. And then 2 will be single parameter or persistent homology with 1 parameter. And then the last part of the talk will be multi-parameter homology. So before we get into it, I just want to talk about some of the uses of this. So what I think is true about this is it's a really beautiful application of tools from pure mathematics, that is algebraic topology, to real world problems. And the level of algebra and topology that's being used is not incredibly sophisticated. So you're not working in some, n categories and things like that. It's quite down to earth. And so I should mention some of the applications where this has been used. It's been used in the study of viral evolution, in the study of breast cancer pathology, and in visual cortex activity, and then many other applications. But the point, I think, lots of times for those of us that come from a pure mathematics background, we think, oh, this is, a real world application is maybe using algebra to study approximation theory. But these are sort of very, very concrete problems that do impact public life. And so I think it's great for us as mathematicians when we can point to the value of our discipline in larger society. So that's the game plan and some of the applications. So let's get to it. And the basic idea that underpins all of this is this broad area of topological data analysis. So the idea is it's great because it's very intuitive. So we start out with point cloud data. So we're handed a bunch of points. Now, intrinsically, a bunch of points has no interesting topology because it's just a bunch of points. So I guess, there's topology there perhaps, but we can see when we look at this, we can see that there's a pattern here, right? And so the idea is that X is a union of a set of points. So say P and X of P. So that's what I've got. But what I want to think of is I want to think of this set of points as having been sampled from some space. And so this I'm going to think of X as sampled from a larger space Y, right? And so our mission is to sort of try to tease out information or extract information about the larger space from our data. But as you can see, so we look at this and we say, there's a circle here, right? There's a donut, right? So that's what it looks like. But there's always going to be some noise typically in an application. So here I have this data and some noise. So now we want to extract meaning. So the idea, main idea, is to introduce a parameter epsilon. And this epsilon is going to be the unhealthiness parameter. So what we're going to do is we're going to take all our points and we're going to send them to McDonald's, and they're all going to eat a big McDonald's meal and become obese. So the idea, this is sort of, I'm being facetious here, but the idea is this epsilon parameter is going to be putting a little epsilon ball around each of our points. So this is going to be, we introduce a space x sub epsilon, which is going to be the union again of p element of x of n sub epsilon of p. So all this is doing is for each parameter epsilon, and this epsilon is an element of R. It's the radius of a little ball. So you can see, and this is exactly, I mean, if you were, it's very naive, but it turns out, surprisingly, sometimes naive ideas are not effective, but this naive idea actually works pretty well. So we start to add this parameter. So let's say we add a parameter. So we start battening our balls, right? So we do that. So here's my parameter, I don't know, whatever it is. This is, you know, the size of a coin. So far, things are not connecting. So I make my parameter, still not seeing anything. I make my parameter a little bit bigger. Once I've gotten about that big, at that point, for some value of epsilon, I actually see at this epsilon, say this is epsilon equals, I don't know, who cares? Let's call this 1. We actually see the circle, S1, right? We see it here. And I also have some isolated points from my noise. And then the problem is that as epsilon gets too big, we just see one big blob. Right? Once my epsilon is you know, this big, I just see a big blob. So the idea here is going to be that if epsilon is too small, say 1 over epsilon is big, epsilon's too small, we only see x, right? We don't see anything interesting. If epsilon is too big, then we just see a blob. This is our, I should have just left this x like that. And so there's some happy intermediate values, which are sort of, we have this phrase in English, the Goldilocks zone, right? There's the story of Goldilocks and the 3 bears, where there's mama bear, papa bear, and baby bear. And papa bear is too big, mama bear is too small, and baby bear is just right, or something like that. Anyhow, this is the Goldilocks. This is just right. And for that parameter where it's just right, you actually see the topology, and eventually you fall off, you become too big. So this is the basic setup. And now what I want to do is talk a little bit about, so notice what we have is this is called a filtered topological space. So the formal definition is this is a filtered topological space. And it's because when I change my parameter values, it's clear that if epsilon prime is less than epsilon, then I get an inclusion x sub epsilon prime sitting inside x sub epsilon, right? As the parameter gets larger, my spaces are included. So I have this nested, of course, nested in some sense, this parameter is a real value, this nested sequence of topological space, and that's the filtered topological space. One observation that's kind of crucial that I want to make, and this is for those of you that are not topologically inclined, this might not be so enlightening, but this is very much like Morse theory. So in Morse theory, you study a manifold by introducing a Morse function, and what happens is that Morse function gives you a map from your manifold to the real numbers, and as you vary the value of your Morse function, the topology of sort of the slices of your manifold stays the same most of the time, but at certain critical points of the function, the topology changes. And so the idea is that there's only finite number of points, even if we have a big data set, right? When I have 2 points, those points, they stay disjoint up until a single instance in time when they connect, and the topology changes, right? I change from 2 disjoint points to sort of a single blob here, which topologically, this is where the distinction occurs when those meet. And then that's it, right? So there's only finite points where the topology changes. So even though this is a parameter that lives on the real line, there's really only finite numbers of points, even for a massive data set, where your topology is going to change. So that's a key idea. All right, so that was the motivation, or the sort of intuition. So now I want to talk about two complexes that we're going to build from this. So I'm kind of jumping ahead because I haven't done my basic introduction to algebraic topology yet, but I want to talk about the Rips complex and the Check complex. So the Check complex, we create a K-simplex, and I'm going to talk about simplices in a minute. If I have a set of points for every set of points P sub I0 through P sub ik, so I have a K plus 1 tuple of points, such that the intersection of the n sub epsilon over 2 of the P sub I, P sub ik, K equals, I guess I should P sub ij, J goes from 0 to K, the intersection of this is non-empty. So what this means pictorially is I take an epsilon over 2 ball around each of these K points, and then I close it up. The intersection of all those balls has to be non-empty. So the picture would be something like this. So here's 3 points, and at some point in time, so I want them to, at some point right about here, halfway, these guys meet, but I won't have sort of, if these were equidistant, the pairwise intersection, this won't be a 3 simplex, but at some point in time, when all 3 of these balls overlap, when it gets a little bit bigger, so that all 3 overlap and there's a common intersection point, then this will give me a 3 simplex. So I created a 2 simplex, rather, a triangle. So that's the Check complex. And the other complex that we use is the Rips complex. And here, this corresponds to the same P sub I0, P sub ik, such that, but here, all I need is that the distance from P sub ij to P sub im between any 2 points is less than epsilon. Notice this is epsilon over 2, this is epsilon. And the point is that, so as long as pairwise distances are all less than epsilon, then I create a K-simplex. And so this is actually good or nice theoretically, but hard computationally, because checking that this intersection of balls is non-empty is very, very hard. This is not so good, let's say weaker theoretically, but easy or easier, pretty easy, so pretty easy computationally. So there's advantages to each of these 2 complexes. The point is that these are giving us ways to get simplicial complexes. So now what I want to do is switch gears. So these are the 2 types of complexes that we're going to be interested in. And now I want to switch gears and move to part 1 of the top. I guess I called part, that was, the introduction was part 0. So this is algebraic topology. Turbo version. So we're going to do all of the first, maybe the first 2 weeks or 3 weeks of an algebraic topology course in, I don't know, 15 minutes. So what do we start out with? We start out with a simplex. So definition, an n simplex is an n plus 1 set plus all subsets. So we might do something like this. A 2 simplex, e.g., if n is equal to 2, we might have A, B, C, and then A, B, A, C, B, C, A, B, C. And if you felt like being pedantic, you can include the empty set. We don't need to. So the way that we think of this, though, from a topological perspective, is we think of this as being a triangle. So a triangle, of course, is determined by 3 vertices. So I think of this as A, B, C. Right now, I don't care about the ordering of the vertices, but in a second, we'll introduce the notion of an orientation. So AB, let's get some, this is topology, so we should use colors, right? So AB would be this edge. And of course, a vertex would just be something like, here's the vertex A. So we usually think of these as vertices. We think of this as an edge. And we think of this object as a triangle. Right? So this would be an example of a 2-simplex. A priori, this is simply a combinatorial object, right? We haven't embedded it into a space. But of course, if I actually assign coordinates to these vertices, then I have a realization in some honest, say, Euclidean space. So that's an M-simplex. Or if we add, so now I want to decorate this a little, so I want to put in oriented. So I want to put oriented N-simplex is an n+1 set plus a choice of ordering. So now what I want to do is talk a little bit about this. I'm going to be somewhat cavalier or imprecise about it because I don't want to delve too deeply into the details. But when I say an edge, what I want to picture this edge AB is now I've ordered it. If A is the first element and B is the second, I want to think of this as AB. And I want to think of this as A is the tail and B is the head. So I want to think of that as an orientation. Of course, a vertex doesn't have any orientation. Similarly for a triangle, and this is kind of like a flashback to your vector calculus when you were doing, orientations of surfaces. This is A, B, C, and I want to think of that using the right-hand rule as being sort of a picture like this. A goes to B goes to C. So I want to think of that as the orientation there. And similarly for a tetrahedron, for a 3-simplex, and so on. So that's an oriented simplex. And so now we're going to define, so notice, this is telling us what my simplices are. So I had a data set, I have a bunch of points. This is telling me how to build these. I haven't talked about orientation, right? We haven't talked about an orientation, but it's certainly telling me who my edges and triangles and vertices are. So that's what that data is. It's not oriented yet. So now let's change colors for a little bit to make things livelier. So an simplicial complex, a simplicial complex delta on vertex set V is a collection of subsets of V with the caveat that if sigma is in V and tau is a subset of sigma, then tau is in V, is in delta, sorry. So it's easier to just draw a picture and do an example than to belabor the point. So we might have something like this. So I might have 1, 2, 3, and 2, 4, and 3, 4. And so, and in fact, if I added an oriented here, will just be a choice of oriented collection of with orientations on each of these. So to draw a picture of what this looks like, and I'm leaving out right now the fact that because 1, 2, 3 is there, this is a triangle. If we drew it as an oriented triangle, we'd draw 1, 2, 3, and I could think of this as having orientation there. And then I also have this edge 2, 4. So I have an edge to 4, and I have an edge from 3 to 4. So I also have an edge here. Notice this is sort of filled in So I have a triangle, and then I have two edges. So I have a picture like this. So that's my oriented simplicial complex. What you should keep in mind is that this is somehow, a lot of us, as mathematicians, probably when we were kids, we played with Legos. So this is just like Legos. So the simplices are your building blocks, and you go to your Lego store, you buy a set of Legos, and then you assemble them. And the point is, though, that simplices, when I build my simplicial complex, they have to glue along subsimplices. So I can't do something like take a triangle and glue an edge onto the middle unless there was a vertex here already. So I can't just stick something on to this edge if there's no vertex here. But if there's a vertex there in the middle, I can certainly glue them. So I have to glue simplices together along subsimplices. All right, so that's the data of an oriented simplicial complex. And then the only technical thing I'm going to talk about, and it's not too technical, is that there's an equivalence relation we're going to use. And I'm going to define an equivalence relation. Now I'm going to define an equivalence relation on my oriented simplices via v sub I 0. Let's just start with 1. V sub I 1 up through v sub I k is equivalent to -1 to the sine of some. This is terrible. This is, I hate to use, I used sigma up here. This sigma is going to be a permutation. This sigma is an element of Sk. It's a permutation on k objects times v sub I, or sigma of I1, v of sigma ik. So, and this sine of sigma, a permutation, can be written as a product of transpositions, and the sine of sigma is +1 if this is an even permutation, and -1 if sigma is odd. So what this means in practice, this might seem a little opaque or hard to grasp, but if we think about it, we should always do a simple example. So what this is saying is that this simplex 1, 2, if I flip the order here, that's a single permutation. That is an odd thing because it's a single transposition. This is equal to -2, 1. And the picture that we have intuitively is that if I took the edge, this oriented edge 1, 2, what is 2, 1? 2, 1 is supposed to be, without this is supposed to be tail at 2, head at 1. So this would be this thing. And just like in calculus 1, when I change the orientation of a curve, I have to flip a sign in there, right? So this is exactly saying that this thing is equal to minus this thing, right? And that's what this relation does. So that's an equivalence relation on our simplicial complexes. And I'm going to erase it now. And now we're going to build an algebraic object with these things. So now we're almost done with our algebraic topology 101, but we have one last thing. So now from the data, the input, say, let's do it this way. Now, construction. Input, an oriented simplicial complex delta. The output is a chain complex and a ring. And a ring R, if you like, this R might be the real numbers. It might be the ones that we're going to work with really are going to be some field, polynomial ring in one variable over a field, or polynomial ring in two variables over a field. And you could keep on going. But these are the three that will be of interest to us today. So the output will be a chain complex of R modules. So what does this mean? I'm going to take the ith module Ci of delta comma R is going to be an R module with basis the oriented I simplices of delta modulo this equivalence relation, right? So that's what we've got. So let's do it for this little example. So for the example that we've got on the board, and let's just use, right now, let's let our coefficient ring be the real numbers. So what do we have here? I'm going to have C sub 2, these are my two simplices. I'm going to have one simplices, those are my edges, and then I'm going to have zero simplices, my vertices. So I have four vertices, so this is going to be isomorphic to just r to the 4, and then I have a 0 here. And I should say, these are the objects. We'll talk about the differential, and to be a chain complex means that, and maps between them, and maps boundary I, mapping C sub I delta comma r, C sub I minus 1 of delta comma r, such that boundary I plus 1 is 0. That is, doing the map twice is equal to 0. So C1, we have 1, 2, 3, 4, 5 edges. So this will be isomorphic to r to the 5th. And then we only have a single triangle, so this will just be an r. And then I have these maps. This would be boundary 2. This would be boundary 1. And essentially, I'm going to write down, well, let's just go ahead and do what the definition of the differential is here. So this differential boundary I is defined. I have to tell you, we get handed an I simplex, which is, of course, an I simplex is given by, an oriented I simplex is given by an I plus 1 tuple of the vertices. So boundary I, we have to say what happens when we input an I plus 1 tuple. So let's say we input V sub J0 up through V sub J I, right? That's an I plus 1 tuple. And it is equal to summation K equals 0 to I minus 1 to the K. So it's an alternating sum. And all we do is leave out the K thing. So of V sub J0, V sub JK hat, this means leave that one out, up through V sub JI. So it's an alternating sum of one-dimensional lower things. In particular, let's just do again do this example. The boundary of the simplex 1, 2, 3 is simply minus 1 to the 0. That's a 1. Leave out the first thing. So what I'm going to get 2, 3, right? Leave out the first thing. And I minus 1 to the 0 is just 1. But then leave out the middle thing. That's going to be minus 1 to the 1. So then minus 1, 3 plus 2, 3. Right? So it's an alternating sum of the edges of this simplex. And in particular, perhaps particularly transparent is the boundary. If I do boundary 1 of V0, V1, I just get V1 minus V0, which is exactly the head of an arrow minus the tail, right? So if I had this picture, V0, V1, that's my oriented simplex. The boundary is just the head minus the tail. So this is our differential. An exercise for those of you who are seeing this for the first time is that boundary squared is equal to 0. So we do it twice. I guess I should have said boundary squared is equal to 0. Do it twice to 0. So now, finally, we can define the object of investigation, which is if I have a chain complex, because doing this map twice is 0, this means, of course, that since boundary squared equals 0, the image of boundary sub I plus 1 is contained in the kernel of boundary I, and so we can form the homology. So hi of delta comma r is by definition the image, the kernel of boundary I mod the image boundary I plus 1. All right, so last example that we're going to do. So again, for those of you who are experts in algebraic topology, this is a quick review, but if you don't know any algebraic topology, so as I mentioned, I was talking in the breakout room beforehand. So I taught a month-long class on topological data analysis last month. And my audience consisted of grad students, but they were all from statistics. And so it was kind of important because I mean, topological data analysis, that certainly falls in the realm of statistics. And so understanding the algebra and topology was important for them, but they also needed a review. So let's see example. 2 examples. Let's do this one, 1, 2, 3, versus, and it's oriented. 1, 2, 3. This is hollow. So let's compute the homology of these 2 things. So here, we only have, these are both one-dimensional simplicial complexes. We only have edges and vertices. So here I have 2 edges, so I'll have C1, which is isomorphic to R2 because I have 2 edges, and I'm mapping to C0, which is isomorphic to R3 because I have 3 vertices. In this map, well, my orientation, my map is I have 1, 2 as one edge. My vertices are just 1, 2, 3. I have 2, 3 as my second edge. And the boundary of 1, 2 is just head minus tail. So that's 2 minus 1. So I'm going to get 1 minus 1, 0. Right? That's the boundary map there. This is my boundary 1 map. I guess I should put a 0 on each end. Boundary of this is head minus tail. So that's 1 minus 1, 0. And we can see this matrix obviously has full rank. So the kernel is 0. And we conclude that the H1 of this, let's call this delta 1. Let's call this delta 2. So H1 of delta 1 is 0, and H0 of delta 1. Well, the kernel of this map is everything. It's all of R3. This map has rank 2, so this is going to be isomorphic to an R1. Let's do the same homology computation here. Over here, we've got 0 goes to C1. C0 goes to 0. Same thing, R3. But this time I have 3 edges, so this is R3. Let's write down our little boundary map. My edges are 1, 2, 2, 3, and 3, 1. Notice that the way that this is oriented here, this edge is, the head is 1, the tail is 3, so I've written it that way. And I've got my vertices, 1, 2, 3. So again, boundary of 1, 2 is head minus tail, so head minus tail. Boundary of 2, 3 is head minus tail. Boundary of 3, 1 is head 1 minus tail 3, right? And now we compute the homology. Well, this time we can see if I take and add all these 3 rows together, I get 0, 0, 0. It clearly has rank 2 because this determinant right here is 1. And so this map has rank 2. So it has a kernel. So the kernel of this, which is, of course, the image is 0, the kernel is one-dimensional. So here the H1 of delta 2 is isomorphic to R1. And the H0 of delta 2, again, this map has rank 2. The kernel of this is 3-dimensional, and this is R1. So we already see that this distinction between this simplicial complex and this is plucked out by the homology. It's an easy exercise. If you use field coefficients, that the rank of H0 is going to be the number of connected components. So rank is equal to the number of connected components. Both of these, of course, are connected, so they have one connected component. So we see R1 and R1 here. And this, the H1, the usual way to say this that is presented in an algebraic topology course is that H1 is counting the number of incontractable circles. So here, topologically, this is just an S1, right? This is just a plain old circle, and I can't contract it down to a point. I can't homotope it down to a point. And so the point is that this H1 is counting the fact that this is a circle. So this captures the fact that there's a circle. If you've never done this before, it's a good exercise to do this for, a torus. And when you compute the homology for a torus, you'll get that H2 is one-dimensional. I guess I should use little h's for dimensions. H1 is 2-dimensional and H0 is one-dimensional. And it's because there's these 2 incontractable circles here on the torus. There's that one and that one. Whereas on S2, on the 2-sphere, we'll compute any circle smoothly homotopes down to a point. So we're going to get that H1 of the 2-sphere is 0, but H2, which is going to be incontractable 2 spheres, that's going to be 1, and H0 is 1. And this is, of course, we're seeing point Carré duality, the symmetry of the Betti numbers. All right, so that was our, maybe it was more than 15 minutes. I might have done 20 minutes, but now we are now all experts in algebraic topology. And what we're going to do is we're going to go back and apply this. So we want to apply our tool to either the check complex or the Rips complex, right? And the point is that both of these, the check complex and the Rips complex, they gave us simplicial complexes. And what they don't give us is an orientation, but typically topologically what you're given is the space without an orientation. You choose an orientation and you compute with that orientation. And so that's the game. So, so now let's move on to that. And now we're ready to talk about persistent homology. So that was the first, we're halfway done through the talk and we've got about 15 minutes left. So persistent homology. So here's what we're going to do. Part 2, persistent homology. One parameter. So, so the key point here is we have our filtered topological space, right? So what we have this filtered topological space, x sub epsilon prime contained in x sub epsilon if epsilon prime is less than epsilon, right? And we know that changes in topology of these spaces occur only at a finite finite number of values of epsilon. So essentially what we're going to do is discretize this. So we discretize this. So what's going to happen is at certain values, so I'm going to think of this epsilon. So the way to, and this is the part that takes, that will take a little bit of thinking on the part of the audience. Or I should say, let me put an aside here, nice introductions to this. To persistent homology. I'm going to write PH for persistent homology. There's Bulletin of the AMS, intros by Rob Geist and Gunnar Carlsson. Also a nice notices article, which discusses more this Morse theoretic perspective that I mentioned by Shmuel Weinberger. So those are some good articles to start. And then there's also, if you want, there's 8 lectures on my website. So I taught a course, as I mentioned, on this last month. Anyhow, so we discretize. And so the point's going to, what's going to happen is that our modules will be over R of epsilon, and I'm going to write this R of epsilon as R of x. And so now the point here is a key theorem in algebra is that R of x is a principal ideal domain. So what does this mean? So a ring is an integral domain if it has no zero divisors. So polynomials with real coefficients are certainly an integral domain. If you take 2 polynomials and you multiply them together and you get 0, the only way that can happen is if one of the polynomials is 0. So this is R of x is a domain. An ideal is a principal, or a ring is a principal ideal domain if every ideal. So an ideal is to ring. Essentially, the analogy, if you're not an algebraist, is that an ideal is like a vector subspace of the ring, in the sense that an ideal is a subset. This is a subset of my ring, which is closed under addition. That is, I can add two elements of the ideal and I get something. So in this sense, it's like a subspace, because in a subspace of a vector space, I can add vectors and I get something back in subspace, and it absorbs multiplication by an element of the ring, right? And so again, this is exactly like in my loose analogy, like a subspace of vector space. So this is an ideal. So, and every ideal is generated by a single element. That's what principal means. So this is a principal ideal domain. So in particular, an obvious example of if I took a polynomial ring in two variables, this is not a principal ideal domain, because I can take the ideal generated by x and y. What does this consist of? This consists of all polynomial combinations where I take some polynomial f1 of xy and I multiply it by x, and I take some other polynomial f2 of xy and I multiply it by y. I need both x and y to generate this ideal. So this is not a principal ideal. So there's something, the point is that there's something very, very special about polynomial rings in one variable. All right. And so now the key theorem, this was not a theorem, this is a definition of a type of ring. A key theorem in algebra is that any finitely generated module over a principal ideal domain, that's what I'm going to write this as PID, decomposes, let's give the module a name, M over PAD is isomorphic to a bunch of copies of the ring. So I'm going to write M is isomorphic to R to the K. So this is just a number of copies of my underlying ring R over a PID R. Direct sum I equals 1. Let's say this was K1, R to K2 of R mod an ideal, let's say PI. Right? So, and that's because every ideal, so if this is usually called the torsion component, because this PI is a torsion element, right? If I have the one here, P kills one in here, and then this is the free bit. So this is the free part. All right. So what's the point? Why would we care about this? So the point is that our homology, because our chain complex is going to have the structure of modules over this, our homology modules will also have the structure of modules over R of x. So the point is, in our chain complex, whichever one we build the check, or RIPS complex, has the structure STR UCT of modules over R of x. So the homology will decompose as below, as star. So star is this. This is, you guys, I'm glad that people aren't unmuting themselves and yelling at me, because my writing, I know, is pretty bad. It looks like I'm off. I'm just right at the edge of the board there too. So the point is that a finitely generated module over a principal ideal domain has a number of components that are just copies of the ring, and a number of components that are copies of the ring modulo an ideal. So torsion and free part. All right. So so now I want to talk about how this is usually displayed. So let's just say, so suppose we have an H1 that decomposes as, and now the other thing to notice is that when we have this parameter epsilon, so this is our x equals, so I've discretized epsilon to be x, and the point is that there's only finite numbers of places where the homology changes, and I want to use the multiplication by x to encode where that homology changes. So HI is going to be isomorphic to some number of copies of R and some number of copies of R in my ring. This is R mod some ideal I. So the thing is that what's happening here is, if you remember, we had these homology classes, right? So I might have something that was 3 separate points, and at some point those points join together. Maybe I had 4 points to form a circle, right? So an S1 appears, and we're going to look at H1, right? So at some point in time, I have a homology class that appears. So let's say that homology class appears here, right? That's where this class was born. These guys all touch. But then at some point later on, they all coalesce into a point. So that cohomology class is going to die. And this is exactly what I said about a homology class appears at a certain point in time, x. Maybe this is x to the I. And then at some point they coalesce. And they coalesce over here at x to the I plus j. So what's going to happen then is one of these summands, this is going to, this interval that represented the birth, this is usually called birth, and this is called death. Obvious reasons, the homology class appeared here, it dies over here. And so over here in this module, this would be something like, this would not something like, it's exactly x to the I. That's a generator, that's like that's a single generator is isomorphic to my ring, there's no relation. But then the relation I'm modding out by x to the I plus j. So this is exactly one of these torsion components. But the other thing that could happen, and remember, we're going to always stop before we turn into a huge ball. I might also have some class that never died. So it lasted forever. It never died. So it was born over here, but it didn't die. And so this will correspond to one of the free summands. It has, but notice this free summand is going to look like, let's call this, it was born at time x to the k. So this is just going to be x to the k, but there's never a relation on it. I never killed it off. And so what you'll see when you look at these introductory articles on persistent homology is that persistent homology is encoded, pH gives you a barcode. And so you see these little diagrams that look some picture like this, and you have little short bars, maybe a long bar, another short bar, short bars, longer bar, maybe short bar over here, another long bar, like this. And so what this is representing is exactly this decomposition. This is just representing that H1 decomposes as 1, 2, 3, 4, 5, 6 torsion components. This would be 6 torsion components equals some direct sum, I equals 1 to 6 of x to the k sub I modulo x to the k sub I plus k prime sub I, right? This is birth time, death time for these little short things. And then there's 2 other components of x to the j sub I, right? So these 2 components here and here that never had a death. So these are the long bars. So these are called long bars. These are short bars. And the intuition is that short bars come from noise. So the intuition is that short bars are supposed to come from noise. The intuition is that short bars and the long bars represent features. And this is where the persistent word comes from, P-E-R-S-I-S-T-E-N-T, because they persist. So the whole idea of persistent homology really comes down to this structure theorem from algebra, that we build this filtered simplicial complex, that at only certain points in time do we have the topology change. Those certain points in time, we're going to use a discrete parameter, right? The discrete parameters are I'm using x, it's born at time x to the k, and maybe it goes on forever, or it's born at time x to the I, it dies at time x to the I plus j. And so we get this nice decomposition from this classical algebraic theorem. So that's persistent homology. It's now about 20 years old. I would be really a terrible speaker if I didn't give credit to the originators of the theory. So PH originated, PH about 2000, and work of Zomorodian, Adelsbrunner, and Letcher. And then it's further been developed by many people. I would refer to the references that I mentioned earlier. And then about 10 years later, maybe around 2010, Carlsson and Zomorodian introduced multiparameter persistent homology. So in the last, I see I'm actually already over time. So I'm going to do 2 minutes of an overview of multiparameter persistence, and then I'll shut down. I'm sorry, I'm already kind of running up to the edge. Maybe I did too much introduction and not enough meat. So the idea of multiparameter persistent homology is that you might have, suppose your data is evolving in time. So we have that point cloud data, but we have snapshots at different points in time. So the point cloud data is evolving in time. So now I have two parameters. I have the fattening parameter for my point cloud data, but I also have a time parameter. So there's no reason that you can't have a family of simplicial complexes that depends on more than one parameter. So this is, here's a little example of such a thing. So suppose that we have simplicial complexes that depend on two parameters. So here's a family of such simplicial complexes. So it's evolving in time. So I started out with 4 dots. Here I added a 5th dot and I added some edges. And so this is the filtered simplicial complex. Same one over here. Add a line this way. So I'm evolving in time, right? I'm evolving in time in both directions. Notice this dot here, added here, it's going to propagate. So once I add a feature, it propagates in sort of a light cone direction like that. Notice this vertex appears for the first time right here. Once this vertex appeared right here, it's going to propagate over here, and so on. All right. So this is an example from Carlsson and Zomorodian's paper here of a bifiltered simplicial complex. So I have two parameters, a parameter moving this way, a parameter moving this way. So I want to think of this as, say, position 0, 0, 1, 0, 2, 0, 3, 0. This is 0, 0, of course, still here. This is position 0, 1, and 0, 2. So this would be position 1, 1, right? So I have, and notice the point is that we had our point cloud data. There's only finite numbers of points where our topology changes. So what we've done is we've encoded those finite number of points in this nice discrete picture, right? And then I'm going to add a parameter here. This is going to be my x2 variable where things change here. This is my x1 variable here. So now we get a a differential on this complex. And what I want to do, I want to label just one of these little things, and you'll see exactly how it's working. So I want to call this vertex B. So B appeared over here. I want to call this vertex A. A appears right here for the first time. And I want to look at this edge. So the edge from A to B first appears right here, AB, edge AB. So what is the boundary of the edge AB? Well, without having this extra data, the boundary of edge AB is just going to be B minus A, head minus tail, right? But what I want to do now is I want to factor in this extra data that I have, the filtration data. And so the point is, AB, this edge appears in a degree, right? The x2 degree, I guess that's x1, stupid me, it should really be x1, it should be x2. This appears in x1 degree 1 and x2 degree 2, right? This edge appeared right here. So this has weight 1, 2, where it first appeared, which I'm going to write as x1, x2 squared. On the other hand, B, this vertex, first appeared over here in degree 0, 0. So B has weight 0, 0. A, the vertex A, appears right here in degree 1, 1. This has weight 1, 1. And so the point is, what I want the gradings to match up. And so because this has weight 1, 2, I want each of these things to have 1, 2. So this is 0, 0. So I have to multiply this thing by x1, x2 squared. Now, this has weight 0, 0. This has weight 1, 2. That's okay. This has weight 1, 1. I want it to have weight 1, 2. So I'm going to multiply this thing by x2, right? And so this extra data of the filtration gives you a grading here. And so what's going to happen in multi-parameter persistent homology, it's still just same old usual homology. Boundary of AB is B minus A, except that we're decorating them with polynomials. And so the point is that this will give us a chain complex. But now the differentials are going to have, the differentials will have polynomials in x1, x2, right? So they're going to be in 2 variables. And so the point is that this is exactly the realm of algebraic geometry or commutative algebra. So we get a chain complex of modules over R of x1, x2. And then you can apply the tools of algebraic geometry and commutative algebra to study, or homological algebra to study that. And this is what I did. I should mention some joint work with Heather Harrington, Nina Otter, and Ulrika Tillman, all at Oxford. Actually, Nina is now at UCLA. So there's a paper that we published last year in the SIAM Journal of Applied Algebra and Geometry, and we're building on this. But the point is that you go from this very concrete problem in analyzing point cloud data to the realm of algebraic geometry and commutative algebra, which I think is very nice. So that's a good place to end. I'm sorry I went almost 8 minutes overtime, which is terrible, but it's the last talk of the day. And I did say that everybody should have a glass of wine. So I'm still drinking my coffee here, but I'm going to switch soon. So good place to stop and take questions.
So I have a question.
Yes.
If you have more than one parameter, can they have relations between them?
Yes, great question. So the one thing that is going to happen, that's a subtle point here, is that as the data evolves in 2 directions. So the first thing is, in this picture, this is what Carlsson and Zomorodian call a one critical filtration. So when a new feature entered, a new feature entered here, it only entered at one place, but there's no reason here that this thing couldn't also have entered over here. So you could have features entering at several points. And so there's some topological tricks that you can do to turn such a filtration into a one critical filtration. But you can have features entering at different points. Was that, that might not have been your question.
No, yeah, it's okay. It answered my question. And okay, let me see. So we have a question from YouTube. Vinicius asked, Can you give a clue on how the multigraded Hilbert series and multigraded local cohomology comes into play?
Yeah, so the thing that I've completely suppressed here, what's interesting is, so when you work with a graded ring, so polynomial rings are graded ring, is a type of graded ring. Polynomial ring is graded. And we usually use a Z grading, right? So we typically would say that in this ring, x1 squared has weight 2 and x1, x2 also has weight 2, right? These are all degree 2. So this is a Z graded ring. I'm not going to write down the definition of a Z graded ring because this is just a question and answer period. What turns out to be the case is that in multiparameter, and of course you can have more than 2 parameters, it's just that you already start to see the pattern with 2, is that you don't just use a Z grading, we use a fine grading. So in this case, we're going to use a Z2 grading. So the Z2 grading is exactly, if we had something like this, this would have weight 2, 0, right? Because it's 2 in the x1 and 0 in weight in the second, whereas x1, x2 would have weight 1, 1. And so the point is that when you're working in this fine graded polynomial ring, which pops up quite often actually in combinatorics. So if you take a look at Stanley's book on combinatorics and commutative algebra, the Z to the n grading is very useful in combinatorics. What turns out to be the case is that this grading is so fine. I mean, if you think about it, how many polynomials are there of degree 1, 1 that are graded? There's only one. It's only this monomial. There's nothing else of degree 1, 1. So this multigrading, which is the finest possible grading you could have, imposes amazing restrictions on your Hilbert series. And so the Hilbert series is multigraded, but because it's Z to the n graded, what turns out to be the case is that for these homology modules, the Z to the n grading, and this is not, there's nothing topological about this at all. That's what's kind of interesting, is that the Z to the n grading means that the associated primes, actually, let me just do the proof is trivial. So this Z to the n grading, what are the Z to the n graded ideals? They're just monomial ideals. Because the only homogeneous polynomials are monomials. So Z to the n graded ideals have to be monomial ideals. But then what is a Z to the n graded prime? So a Z to the n graded prime is going to have to be a prime monomial ideal. But what are the prime monomial ideals? The only prime monomial ideals are subsets of the variables x sub I 1 through x sub I k. So this is hugely restrictive. This says now when you start analyzing, so we've got a chain complex, but when we start analyzing local cohomology or associated primes or any of those things, we're hugely restricted. In particular, what this says is that when I look at the support of a module, which are the set of primes where when you localize it, it doesn't disappear, those primes have to be coordinate subspaces. So so one of the questions Carlsson and Zomorodian asked that was a motivation for our work was, what can you say in this multigraded setting? And what's interesting is that this multigraded setting is so restrictive that all the associated primes have to be coordinate subspaces. So when you look at some, if you're looking at some HI, which a priori is just some weird module, you know that this thing is going to be supported. Suppose we're in 3 dimensions, right? Suppose we're in 3D. Well, if we're in 3D, this thing can only be supported along, say, a coordinate line, or maybe a coordinate plane, or maybe the whole space. And the analog, right, in single parameter persistent homology, we had the free summand, which lived forever, and then some torsion stuff, right? And this died. So the analog here, the analog of the free summand is something that lives on the whole space. But then instead of just torsion, we have stuff that lives on a 2-dimensional plane, or the stuff that lives along a line. But you still have a very nice way to quantify the size of the homology in terms of what lives on the whole space, that's like the free stuff, what lives just along a 2-dimensional plane, what lives along a line, and so on. So that was a long-winded response, probably way more than you wanted, but that's the intuition there. And it's just that fine gradings impose huge restrictions on you.
Okay, we have another question from Maral. She says that the chain complex C you just defined looks like the Koszul complex. No,
not quite. So the problem is already right here. you can see you're not just getting variables. So in this differential here, I'd have an x1, x2 squared, and an x2, right? So it's not a Koszul complex. And in particular, the Koszul complex, I mean, oh, I see. So if we just said, if we treated these things like, I see it, Koszul, no, it's not. So I understand the question, it's not. So it's not just, it's a little, I guess the right way to say it is that when you look at the shapes of the differentials look sort of Koszuli. So here, right, the boundary of an edge is 2 things. The next step will be the boundary of a triangle. That'll be 3 things. And so that is like the entries in a Koszul complex, but it's not just a Koszul complex on this thing. So otherwise you'd be just computing Koszul homology of this thing, and that's not what you're doing. It's not a bad analogy, but that's not what it is.
Okay, I think she was comparing the Koszul complex to the Czech complex from community algebra.
That's right. That is a standard. The Koszul and Czech complex are essentially the same thing in the right context. But this is not, so I guess what I should say is this is not that Czech, the Czech, when I was talking about the Czech complex that we build, that's a topological thing. That's not the differentials in the algebraic sort of Czech complex, I'd say.
Okay, I think these were all the questions. Thank you, Hal, for accepting the invitation.
Well, thanks, guys. And I hope that you have a really, or have had a good week so far. And I hope to see you all down the road. And I'm going to come back to Brazil to visit again. So everybody stay healthy, and congratulations too on doing the work to organize this. I think it's great. You guys are taking the initiative. So cheers.